Hi everyone, welcome to my channel. Today we are about to see the next module of the port side truss. The P3-P4 truss segment. Let's start the video. The P3-P4 truss, part of the Integrated Truss Structure (ITS) of the International Space Station, plays a significant role in providing structural integrity. It supports various components and gives the ISS its shape. Much like how an airplane's fuselage supports the aircraft's body, wings, and tails and defines its structure. The Integrated Truss Structure consists of 11 segments. We have already discussed the P6, S0, S1 and the P1 segments. Now let's take a closer look at the fifth segment to be installed on the ISS, which is the P3 or P4 truss. The P3-P4 truss segments provide power using its solar panels and structural integrity to the ISS, and houses heat dissipation systems, especially radiators to maintain heat in the ISS. These thermal regulations and power generation is crucial for managing internal temperatures, preventing equipment from overheating and maintaining a habitable environment for astronauts, and provides electricity for essential equipments. The intricate network of thermal loops, radiators helps efficiently transferring heat away from the station's vital components into space. Manufacturing the P3-P4 truss for the ISS involved a collaborative effort among multiple entities. Companies like Boeing, with facilities in Huntington Beach, California, and Michoud Assembly Facility in New Orleans, Louisiana, played key roles in manufacturing these components. Additionally, Marshall Space Flight Center in Huntsville, Alabama, and other facilities contributed to the production and assembly of the truss segments. Specifically, the solar panels and its subsystems were manufactured by Lockheed Martin. The assembly and integration of these truss segments took place at Kennedy Space Center, Space Station Processing Facility, where final checks and preparations were conducted before launch. The P3 or P4 truss segment was launched as part of the ISS Assembly Mission 12A STS-115 using Shuttle Atlantis. On August 25, 2006, during the first launch attempt, a powerful lightning strike hit the launch pad, leading to a 24-hour postponement to assess any damage. The launch was further delayed by the approaching Hurricane Ernesto. Atlantis was initially rolled back to the VAB but was moved back to the launch pad after forecasts showed the storm would be less severe than anticipated. Following inspection, the launch was rescheduled to September 6th. On September 6, NASA decided to postpone the launch attempt that was already postponed for Thursday, September 7 to September 8, 2006. On September 8, a technical issue arose when one of the engine cutoff eco sensors in the external tank failed. NASA announced a 24-hour delay to address the problem and drain the fuel from the external tank. The faulty sensor, eco sensor number 3, incorrectly indicated that liquid hydrogen remained in the tank despite it being empty. However, the other 3 eco sensors showed a dry tank, and NASA determined that a launch with 3 functional sensors was feasible. The launch finally took place on September 9, 2006 at 11:15 EDT. With all eco sensors functioning correctly, Atlantis lifted off successfully.
Up and burning. 2, 1, and liftoff of Space Shuttle Atlantis, opening a new chapter in the completion of the International Space Station for the collaboration of nations in space. Roll programming.
Roger, roll, Atlantis.
Houston is now controlling. Roll maneuver is underway. Atlantis is heading into a heads-down position on course for a 51.6 degree 137 by 36 statute mile orbit. Atlantis already 2 miles downrange from the Kennedy Space Center at an altitude of 2.8 statute miles. Now at 72%, beginning to throttle back up as the vehicle passes through the...
During ascent, Mission Control instructed the crew to address ice buildup in the cooling system, which they managed to resolve. Following the main engine cutoff, Atlantis' crew used cameras to document the separation of the external tank, and the images were sent to Earth for analysis. Once in orbit, the crew aboard Atlantis initiated a comprehensive inspection of the spacecraft using the Orbital Boom Sensor System, a 15-meter extension for the shuttle's robotic arm. Astronauts carefully examined the reinforced carbon-to-carbon panels on the shuttle's wings and nose cap. This inspection was crucial for ensuring the shuttle's integrity before docking with the International Space Station ISS and performing their planned spacewalks. On September 11, 2006, Atlantis performed an orbital backflip maneuver about 180 meters below the ISS, enabling the station's crew to capture high-resolution images of the shuttle's heat shield. This maneuver provided valuable data on the shuttle's condition and was the key step before docking. Atlantis successfully docked with the ISS, and the hatch between the two spacecraft was opened 2 hours later. Following the docking of Atlantis with the International Space Station ISS, the crew initiated the installation of the P3 or P4 truss segment. The shuttle's robotic arm, Canadarm, lifted the 17.5-ton truss from its berth in the payload bay and maneuvered it into position for handover to the station's Canadarm2. The transfer was executed smoothly, with the station's arm taking over to complete the attachment of the truss segment to the ISS. During the subsequent spacewalks, astronauts perform critical tasks to integrate and activate the new truss. On day 4, they focused on installing power and data cables, releasing launch restraints, and preparing the truss for operational use. This spacewalk exceeded expectations, allowing astronauts to complete additional tasks initially scheduled for later spacewalks. The following days saw further spacewalks, including the activation of Solar Alpha Rotary Joint (SARJ) and the deployment of the solar arrays. After the spacewalk, the crew prepared for undocking procedures. On flight day 9, Atlantis undocked from the ISS, concluding the tasks at the station. The crew continued final inspections of Atlantis' heat shield in preparation for re-entry on flight day 12. Flight day 13 marked the end of the mission, with Atlantis completing its re-entry and landing at Kennedy Space Center Space Shuttle Landing Facility. The successful mission contributed to the ongoing assembly and enhancing the International Space Station, showcasing the collaborative efforts of NASA and its partners in space exploration. The P3 or P4 system includes many necessary parts for the functionality of the ISS. Now let's see about each system and parts under them. Power generation system. The power generation system of the P3 or P4 truss segment encompasses a crucial component vital for supplying electrical power to the International Space Station ISS. The solar array alpha rotary joint SARJ serves as a mechanism enabling the rotation of the solar arrays, ensuring they consistently face the sun to optimize energy production. Complementing the SARJ, batteries are utilized for storing excess electrical energy generated by the solar arrays during periods when the station is not exposed to direct sunlight, ensuring continuous power supply to the ISS during orbital nighttime. Control and management. Managing the operation and coordination of key subsystems, the control and management system of the P3 or P4 truss segment features several vital components. The solar array alpha rotary joint SARJ drive lock assembly plays a crucial role in securing and controlling the rotation of the SARJ, ensuring optimal alignment of the solar arrays for maximum power generation. Furthermore, the photovoltaic radiator PVR controller unit serves as a central control unit for managing the operation of the solar arrays radiators, regulating power distribution and thermal management within the truss structure. The P3 or P4 truss segment has dimensions of approximately 13.8 meters, 45 feet in length, 4.9 meters, 16 feet in diameter, and a total mass of 15,900 kilograms, 35,050 pounds. In conclusion, the P3 or P4 truss segment plays a pivotal role in the structural integrity, power generation, and mobility of the International Space Station ISS. through its intricate systems and components including the solar arrays, alpha rotary joints, Sarge, batteries, solar array wings, radiators, Sarge drive lock assemblies and PVR controller unit. The P3 or P4 truss segment embodies the collaborative efforts of international space agencies in advancing space exploration and scientific research. As humanity continues to expand its presence beyond Earth's atmosphere, the significance of such engineering marvels underscores our collective pursuit of knowledge and exploration in the vast expanse of space. I hope this video on the P3 or P4 truss segment was interesting and informative. I'll meet you in the next video with another interesting ISS module. Take care, bye.